Hello, my name is Tom Maullin. I'm a postdoctorate researcher working at the University of Oxford under the Nuffield Department of Population Health. In this video, I will be demonstrating how to assess spatial uncertainty in task-based bold fMRI data by using confidence regions. This practical was originally presented as part of the OHBM 2023 Advances in Statistical Neuroimaging educational course. Okay, so to get started, open a browser and navigate to the CR Toolbox demo repository. A link for this repository should now be appearing on screen. Once you're at this repository, find the CR demo instructions.pdf file. Inside this file, you'll find instructions on how to download today's work. To get started, you'll need to open a terminal and type pip install notebook. Once this is installed, navigate to somewhere you want to save your work for the day and clone the repository shown here. Okay. This will download the work for today. Once that's downloaded, change directory into the repository and run the following command to run the Jupyter notebook. This will now open in the browser the Jupyter notebook which we'll be working with today. If for any reason it doesn't, you can always look over here and find the URL to open in the output on the terminal. We're now ready to start working through the practical. This practical will introduce you to the concept of CRs, or confidence regions, and show you how they may be used to make inference about fMRI bold signal. In this session, you'll gain an understanding of what CRs are, both conceptually and mathematically, when you may want to use CRs and why, the factors that influence the shape and size of CRs, as well as common pitfalls with interpreting CRs. We'll also cover what software is available to generate CRs, in particular the CR toolbox, and we'll frame this within the recent debate about null hypothesis significance testing in neuroimaging. If you have any questions, please feel free to reach out to me at tommaullin@gmail.com, and an anonymous feedback form is also available, a link for which should now be appearing on the screen. Okay, we'll start by installing the necessary Python packages using pip and then importing these into our workspace. The package we'll be focused on today is the CR toolbox, which we will be using to generate confidence regions. We'll start out by considering a simple signal plus noise model. This model will take the form y of s equals mu of s plus epsilon of s, where s can be thought of as a spatial location, e.g. a voxel, y of s can be thought of as the vector of observed values at that voxel, mu of s can be thought of as the signal we wish to estimate, and epsilon of s is the noise process, which we'll typically assume to be Gaussian with variance sigma squared of s. We want to estimate the excursion set AC, which is defined as the set of spatial locations over which mu of s exceeds c. In the context of task-based fMRI, this would be the brain regions over which percentage bold change exceeds some predefined threshold, e.g. 1%. A brief illustration is provided here, showing bold signal as a blue surface, which we threshold to obtain the yellow brain regions AC. On the right-hand panel, you'll see some illustrations of potential confidence regions for AC. Confidence regions may be thought of as probabilistic sets which in some sense bound AC. So here we see that AC hat plus is nested inside AC, and AC is nested inside AC hat minus. We'll define this more rigorously shortly. Of course, in practice, we can't look at the true signal, so we have to estimate AC. Our point estimate, which we'll denote as AC hat, is defined as the set of spatial locations over which our estimate of mu hat, exceeds C. To make this more concrete, we'll look at some example data. In particular, we'll start by looking at some simulated data designed to resemble the bold response for a single subject. In the CR toolbox, you can view volumetric data using the display volume function. This will open an interactive display, allowing you to scroll through the slices of the image. Here we have an interactive view of a simulated bold response for a single subject given in sagittal view. It's important to note here that opening many views into nifty images can be quite memory intensive, so we strongly recommend that once you're done viewing an image, you close the viewer by clearing the cell output. You can do this by navigating to Cell, Current Outputs, and Clear. If you want to keep a display open for reference, the display volume function also has a simple setting, which allows you to specify a single slice and show it in a non-interactive view. In the model we gave above, if S is the location of a voxel, you can think of Y of S as the vector constructed by going through the subject level bold images one by one, extracting the bold response from each and stacking them together into a vector. We'll now look at the signal mu used to generate this data. To do so, we'll read in a file representing the true signal and a mask file to help us visualize the data. Here is the result. As can be seen in this image, this simulation uses a single spherical cluster of activation, located near the center of the brain. The set AC, which we wish to estimate, is the binary region over which mu exceeds C. In this instance, we have chosen C equal to 2, and the resulting binary set looks as follows. Again, we can see there's a single spherical cluster of activation near the center of the brain. In the next few sections, we shall use these example datasets to explain what CRs are and demonstrate some basic properties of CRs. Before going further, we'll briefly discuss some motivation for using confidence regions instead of current, more conventional approaches such as hypothesis testing. Although hypothesis testing is commonly used for fMRI analysis, it has received many valid criticisms. Objections to hypothesis testing include the null hypothesis fallacy, which is the idea that even tiny effects can be determined significant for large enough data, the arbitrary nature of choosing a significance value, the fact that observing a non-zero effect tells you nothing about the size of the effect itself, and other inherent limitations. The American clinical psychologist Paul E. summarized the problem as follows. The problem is epistemology, not statistics. Replace significance tests by confidence intervals and quantify accuracy of risky numerical predictions. The same comment applies here in higher dimensions. We want to replace or at least complement significance tests with confidence regions and effect sizes. We're now ready to explain what confidence regions are. You can think of confidence regions as like confidence intervals, but in higher dimensions. In the same way that a confidence interval provides an upper and lower bound for a scalar parameter, confidence regions provide inner and outer bounds for estimated clusters. For instance, here we have two confidence intervals for a scalar parameter A. The interval on the left is wide, indicating the parameter estimate might not be very reliable, whilst the interval on the right is tight, indicating a high reliability in the parameter estimation procedure. The same idea applies here for confidence regions. Here we have two sets of confidence regions for our set AC. On the left, the confidence regions exhibit very little resemblance, indicating the estimation process might not be very reliable, whilst on the right, the confidence regions are tight, indicating a high reliability. Throughout this tutorial, we shall refer to the outer confidence region, indicated here in blue, as AC hat minus, and the inner confidence region, in red, as AC hat plus. Mathematically, we say that the probability that confidence regions are appropriately nested is equal to 1 minus alpha, for some confidence level alpha. This is directly analogous to the definition of confidence intervals. In the following, we should take alpha to equal 5%. Let's now have a look at some pre-computed confidence regions generated using the simulated data. We can do this in the CR toolbox using the display CRs function. As can be seen in this image, the estimate of AC, shown in yellow, is very noisy and identifies many regions other than our simulated signal. However, the inner confidence region, AC hat plus, shown in red, identifies very little, mainly showing only the region in which we actually generated signal. We can interpret this as saying that although the point estimate AC hat identified many regions of activation, only those confirmed by AC hat minus are likely reliable. As with the display volume function, we highly recommend clearing the output of the display CRs function when you are not looking at it. Again, you can do this by just cell, current outputs, and clear. You can also use the simple view in the display CRs function to retain an image of a single slice. At the end of this section, there's a test your understanding box, which will ask you to load in another set of confidence regions, display them, and assess which set of confidence regions gives you the better results. When thinking about this task, it's worth considering the resemblance between the red and blue sets and what this means for the analysis results. It is worth quickly discussing some common pitfalls in interpreting confidence regions. In general, if you generate 95% confidence regions, this does not mean that there is a 95% probability that AC is nested between the specific pair of confidence regions you have generated. Instead, it means that if you generated confidence regions over and over again in the future, 95% of confidence regions which you generate would correctly contain AC. Having 95% confidence also does not mean that 95% of the subjects will have bold activation correctly nested between the confidence regions. Nor does it mean that a given pair of confidence regions generated from a single run of the method will contain the estimate of AC 95% of the time. Instead, a correct interpretation of confidence regions is as follows. If we generated 95% confidence regions numerous times on different samples, the proportion of confidence regions that correctly enclose AC would tend to 95%. Another correct interpretation is that there is a 95% probability that the region between the confidence regions will fully encompass the boundary of AC in some future experiment. And finally, in bold fMRI, the 95% upper confidence region can be interpreted as the region over which we are 95% confident there has been at least a C% change in bold response. We'll now discuss the maths behind confidence regions. If this is not something that interests you, you can safely skip this section and move on to the 2D simulated examples. Several methods have been suggested for generating confidence regions. Common approaches to generating confidence regions include looking at the Hausdorff distance between estimated sets using bootstrap procedures, representing excursion sets using a parametric family and applying sequential importance sampling to estimate probabilities, and using the properties of the noise process along the boundary of AC to assess the probability that the confidence regions are correctly nested. This last method is the one that we favour, and it was originally proposed by Sommerfeld, Sain and Schwartzman in 2017. We shall refer to their work as SSS after the author's initials for short. In SSS, a functional central limit theorem is assumed for mu hat minus mu over sigma over root n, with some limiting random variable g, which is typically assumed to be a unit variance, mean zero Gaussian random field. SSS shows that if you generate confidence regions as the regions of space over which the standardized difference between mu hat and c exceeds some quantile q, then the following equation holds. Equation 2. This equation states that as n tends to infinity, the probability of the confidence regions being correctly nested tends to the probability that the noise along the boundary has magnitude less than or equal to the quantile q. As a brief aside, if you wish to generate images of the boundary of AC using the CR toolbox, you can do this using the getBoundaryMapCombined function, as shown here. In this image, you can see the boundary of the excursion set we saw in the previous sections. The important thing to note from equation 2 is that to set the probability of the CRs being properly nested to 95%, all we need to do is set this right-hand side probability to 95%. In other words, if we know the distribution of this supremum, this means all we need to do is set Q equal to its 95% quantile. In general, we can estimate the distribution of this supremum using a bootstrap procedure. To summarize, SSS CRs are generated as the standardized difference between the estimated process and C, thresholded using a quantile Q. The probability that SSS CRs are correctly nested is asymptotically equal to the probability that this supremum over here is less than or equal to Q. We can choose Q to satisfy this probability being equal to 1 minus alpha by using a wild T bootstrap using standardized residuals from a regression. In the next section, we'll turn to 2D examples. We're now ready to start generating confidence regions. Creating confidence regions requires bootstrapping, which can consume a lot of time and memory. To make things a bit quicker, we'll start off in this section by working with simulated 2D images. To begin, we'll create a 2D signal mu. In this section, we have prepared 3 example signals for you to try out. The first signal is a circular signal and looks something like this. You can generate this using the circle signal function, and if you want, you can change the circle's radius, peak, magnitude, smoothness, and center. Alternatively, you can generate a square signal using the square signal function, or a linear ramp using the ramp signal function. Both the square signal function and the ramp signal function have similar input options to the circle signal function. Using these functions, you can choose a signal which you want to try out to generate confidence regions for. For this practical, I'm going to use a circle signal with a radius of 20 and a magnitude of 3. So it will look something like this. Once we've decided the signal we want to use, we need to add some noise to obtain simulated data. You can do this with the noise function, which allows you to generate some noise with a specified variance and smoothness. Here is a single instance of noise. For this run, I'm going to use noise with a variance of 2 and the default smoothness. My noise will look something like this. We shall now generate some test data. You can do this using the generate data 2D function, which takes as input your signal, your noise, and an output directory to save your images in. By default, this will generate 100 images. You can look at these images using the same display volume function as before, like so. So here is a single instance of data that I've generated using the signal and mean I showed above. Once we've generated some data, the next step is to obtain a point estimate for our excursion set, AC. For reference, the below box creates a display of the true AC based on the signal we've used to generate the data. As you can see, it's a perfect circle. To generate confidence regions, we now need 3 things. We need a mean image, a standard deviation image, and for each subject we need a residual image. These residuals will be used in a bootstrapping procedure to estimate the quantile which is used to create the confidence regions. We can obtain these images using a standard linear regression, which can be performed using the regression function in the CR toolbox. We'll now take a look at our estimated signal mu hat. As we can see, it strongly resembles the true signal mu, which we showed previously. We can obtain our estimated excursion set, AC hat, by thresholding mu hat, like so. As we can see, it's a fairly good approximation to the true AC we used above. Now that we've generated our simulated data and found our estimated region of activation, we can compute confidence regions. We can do this in the CR toolbox using the generate CRs function, which takes as input our estimated mean, our estimated standard deviation, and the directory we wish to save the files in, as well as the residuals from above, the threshold C, and the confidence level alpha. This may take a few seconds to run on your computer. Once the confidence regions have been generated, we can use the display CRs function to view them. These seem like they have quite a reasonable resemblance. At this point, we now have another test your understanding box. In this box, you are invited to go back and investigate other signal shapes and sizes. Try and work out what you think impacts the observed resemblance between the confidence regions. A brief list of such factors will be given at the end of this section. If you are interested in the math behind confidence regions, we can also obtain the quantile estimate used to generate the confidence regions, which in this case was around 3.35. In fact, if we wanted, we could use the generate CRs method to return a range of quantiles and plot the distribution of the supremum of the absolute value of G. Here is such a plot for this example. We are now ready to move on to fMRI examples and regression. Before moving on, here are some final notes on generating confidence regions. Regression in the CR toolbox can be performed using the regression function. Confidence regions can be generated using the generate CRs function. You may have found from the Test Your Understanding section that the tightness of CR resemblance is influenced by sample size, smoothness, excursion set size, noise magnitude, and noise heterogeneity. This means that each of these factors indicates how reliable your estimated excursion set from the regression is. The performance of the CR method, or in other words, how well it achieves the desired confidence level, is robust to a range of factors such as smoothness, the shape and size of AC, the choice of threshold C, and variation in the noise magnitude. However, the true confidence level may be conservative for small sample sizes. As a quick aside, if you want to investigate the performance of the confidence regions method yourself, you can find some custom code in the extra.py file in the assets folder. If you want to delete the files made by this section, you can run the following box of code. We will now use simulated 3D data to generate confidence regions in a setting that more closely resembles bold fMRI. As a quick warning, in this section we will be generating nifty images, which will consume much more memory than the images of the previous section. If you have limited space on your computer, you may wish to set the number of subjects to a lower number in this section. I'm going to use n equals 100 subjects, but you may need to reduce this if you are short on memory. To start, we will generate some simulated bold fMRI data using the generate data function. This will generate data according to the mass univariate linear regression model, which takes the form y of s equals x beta of s plus epsilon of s. Here, s is again a spatial location, or a voxel. Y of s is our data at that voxel. Beta of s is the parameter vector, and epsilon is our noise term, assumed to be mean zero Gaussian with sigma squared variance. Here is a brief figure illustrating what this model might look like. We can see here that y of s is the bold response vector at voxel s, and x is a fixed design matrix including an intercept and covariates such as age, weight, and BMI. The signal of interest here is beta 0, which may be expressed as the beta vector multiplied by a contrast vector denoted L, which in this case is given as 1, 0, 0, 0. We wish to generate confidence regions for mu, which is equal to L times beta. We'll now have a quick look at some of the data we've just made. Here is a single subject's bold response. As you can see, this highly resembles the simulated data shown previously in the background section. We'll now have a look at the beta map we'll be investigating. As can be seen here, we again have a spherical signal located somewhere underneath the ventricles. As in the 2D example, we will now perform a regression to get estimates of beta, sigma, and a set of residual files. This can again be done using the regression function in the CR toolbox, with the inputs y files, x, and an output directory. After this run, we will no longer need the y files, so you can delete these if you wish to preserve memory. We'll now have a quick look at our estimate of the beta map we're interested in. As can be seen, we do have a reasonable region of activation, again below the ventricles, but it is not as clear-cut as the example we saw previously in 2D. We will now generate confidence regions. We can do this as before using the generate CRs function from the CR toolbox. Please note that running this method in 3D is much more computationally intensive than in 2D, so this may take a few minutes to run. We'll now have a look at some confidence regions for this example. Below this box, we have another test your understanding section. Looking at these confidence regions, try to assess how reliable you think the estimated excursion set is. This brings us to the end of this section, as well as the simulations in general. In the next section, you'll be invited to generate confidence regions for a real-world dataset. If you want to remove the files used by this section, you can use the code shown here. In this section, you are now invited to take what you have learnt and apply it to real-world data derived from the Human Connectome project. Before participating in this section, please ensure that you have signed the HCP data use terms, instructions for which can be found in the HCP Access Form Instructions PDF. The dataset you will be using comes from a working memory task in which 77 subjects were shown various images and then asked to recall them a few moments later. First level analyses have been conducted so that you will have one task-related bold response image per subject. For data protection purposes, further detail on this example will not be included in this video. However, the full example may be accessed online in the notebook once the HCP access form has been signed. We will now move on to the final section, in which we shall generate confidence regions for Cohen's d effect sizes, rather than the bold signal mu. In other words, instead of generating confidence regions for the set AC, defined as the region over which mu exceeds C, we will instead be generating confidence regions for the set DC, defined as the region over which mu divided by sigma exceeds C. The quantity mu over sigma is known as Cohen's d. As might be expected, our estimate of DC hat, is the region over which mu hat divided by sigma hat exceeds C. Using standardized effect sizes of the form mu over sigma may be preferable for many analyses, as the measurement units of mu alone are not always easily interpretable. For instance, in fMRI, percentage bold data undergoes many pre-processing steps, including grand mean scaling and smoothing, making it less obvious what the units of measurement in the final images are. Standardized effect sizes, however, retain the same interpretation, regardless of the measurement units of mu. We'll now generate some 3D simulated data following the signal plus noise model shown in the background section. Again, we can do this using the generate data function. Next, we shall generate the Cohen's d file, transformed residual files that are required to generate Cohen's d confidence regions, and the standard deviation of these images. This can be done using the Cohen's function in the CR toolbox. Here is an image of the true Cohen's d function used to generate these images. This time we have a clear, large region of activation just above the ventricles. Here is our estimate of Cohen's d. This seems to estimate the signal we used fairly reasonably. We will now again use the generate CRs function to make CRs for Cohen's d. Unlike in the previous sections, this time we must give the generate CRs function the estimated Cohen's d instead of the estimated mu, the Cohen's sigma file instead of the standard deviation, and the Cohen's residual files instead of the residual files from the regression. The mode argument must also be set to Cohen's. We will now look at the confidence regions we've generated. These appear to give us a reasonable resemblance in this instance, so we may conclude that our estimated Cohen's d excursion set is reliable. However, as noted in the final test your understanding box, you may find that you need more subjects to get a reliable estimate of the Cohen's excursion sets than you needed for the mean image. To test your understanding, try to answer why you think this might be. The math behind the Cohen's d confidence regions is similar to that of the regular confidence regions, so we won't discuss it in full here. If you want to learn more about this procedure, please see Bowring et al. 2021. To delete the files from this section, you can run this final block of code. This concludes the practical. Thank you for listening.